Hello, everyone. So, welcome back. So, this is second week. I hope that everybody just felt just reasonably okay after the first two lectures and did not get too overwhelmed. So, I want to give you a little bit just some explanation why we are doing something like we are doing right now. So, this is the fifth grade of the Free Asian Math program because the goal is to help students of your age across the whole nation to study some serious math. So I cannot actually assume your background. Perhaps you have been doing very well in math, you're a very strong math student, or perhaps you are not a so strong math students. Maybe your school district is not one of the greatest ones in the nation. Maybe for whatever reason you have been struggling with math, and maybe you waste a lot of time and did not learn much math at all from kindergarten to the fourth grade. I have to assume anything is possible. But in this 1 year, grade 5, my goal is to help everyone, whether you came from not so strong mathematical background or you are already a strong math student, after 1 year, the ground will be leveled. So more or less, everybody will be on the same page. Then we start grade 6, which is officially the middle school. And from there, we'll learn algebra and the more complicated math. So this fifth grade year actually is a critical. If you did not actually learn much math, I want to help you to catch up quickly. That means that you have to fix a lot of things. On the other hand, for those students who have been doing quite well, I don't want you to get bored, right? So this is truly actually a dilemma, how to accommodate both types of students and any type in between. So that's quite a challenge. If I just teach you the math you would regularly see, say, on school math textbooks, there's no way of doing that to meet everybody's expectation. Some people will inevitably get bored. Oh, I learned this 2 years ago, 3 years ago. Why are you talking about this? I'm not interested. So that won't work. But if to make such an advanced student happy, then there will be the danger that students trying to catch up cannot actually catch up. So this is truly a very difficult situation to be in. So my plan is to teach you some math really from a very advanced perspective and very rigorous. More or less, some of the materials will actually be only discussed in the college curriculum. But don't get scared. I have been very careful in terms of choosing what type of materials I will need to present to you. That way, for advanced students, you will definitely learn something that you will never learn in the elementary school because it's so advanced. Only actually high school or college teachers will talk about that, and most likely only college teachers. On the other hand, this is a kind of just really just accelerated and boosted track for those students who want to catch up because we look at some math concept from really very rigorous and very advanced perspective. So that gives you a lot of just freedom to like taking a shortcut, get to the point more quickly and more directly. And that's what we are trying to do now. So if you actually struggled with math in the last couple of years, don't worry. As long as you do all the problems, read the reading handouts, and really invest your time into this, I assure you in 1 year, you will catch up. But the assumption is you have to be serious. At the beginning, if you feel this class is so tough, I just cannot continue, I'm sorry, you are wrong. You definitely can continue. The only thing you need is put in effort. Okay? Even you struggled with math before, this is the right time for you to fix all those issues. I promise. Okay, so last time we started talking about what natural numbers really are. So let's give a very quick review from last time. So we first introduced a few so-called axioms. Axioms are those things that we take as true without actually proving that they are true. They usually is something that is so obvious, so just common sense. Everybody will have to agree they are true. It turns out that there are such things that we can never actually prove. And we will talk about that later and probably talk about those things again next year when we officially start learning geometry. But for now, all you need to know, axioms are just things that we take as true without further just bothering ourselves why they are true. Okay? So this is a set of 4 axioms. They're actually quite simple. Also, number 3 and number 4 a little bit tricky, and if you read the handout, you will understand. So this is the set of axioms that we need for defining the natural numbers. It's in proposition 1.1. So with those axioms, we were able to formally define what natural numbers are. So we start with something that we took as an axiom, that is 0. We all agree 0 is a natural number and it actually represents the initial state of a counting process. Remember in the last set of axioms we just reviewed, there's another one, assume that there's a so-called increment operation on natural numbers. And the most important thing about this increment operation is that it's the same operation that will be applied to all the natural numbers, whether it's a 0 or as we should see 1, 2, 3, they all use this same increment operation. So with those two things, one is the 0, one is the increment operation, we can continuously define what natural numbers are. And this is actually called recursion. So from 0, we define 1. That's just increment upon 0. Then once we have 1, we continue this process. We define 2. 2 is just increment from 1. Okay? And that way, we will be able to define all the natural numbers. And there's no upper bound. This will go on forever. So this is how we actually define natural numbers. So next time, anyone want to challenge you, where are the numbers from? Yeah, we define them. Okay. So from that, we introduce the number line, and we know that number line is a geometrical line which has infinitely many points and it's perfectly dense. So we want to mark on this line all the natural numbers. So we first choose one point arbitrarily, meaning that any point on this line is fine because the line goes to both ends just indefinitely. You can extend the line in both directions just without any limitation. So it doesn't matter when we started. Any point is the same thing anyway. So we choose a point and say this is a 0. Now the next step is a little bit just more care needs to be taken because we still choose an arbitrary point, but we notice there's a direction, either on the left-hand side or right-hand side of 0 because the line goes in both directions. But according to convention, we choose the right side as where the numbers will go bigger and bigger. So we choose another arbitrarily chosen point on the right-hand side of 0 and say this point is 1. Once we have done that, we don't have any other freedom. Why? Because you can see if we once have both 0 and 1, that gives us a so-called unit line segment. Because one line segment, you just need 2 points at both ends. And now we do have both 0 and 1. So this line segment on the line will be called the unit line segment. And it's very important, as we will continue to study today, we call the length of this line segment as the unit length. One question we haven't answered is that what does length mean? What is length of a line segment? Well, for that, we actually do not define it. We just know this is certain quote unquote measurement. Okay, so let's just for now agree on that. So this is a line segment. It does have a length, and this line is right between 0 and 1. And once we have this, now we don't have any other freedom. We can mark 2, 3, 4, 5 only in a way by taking this unit as continuous, adding another one, and continue. If you haven't thought about this, think about this. Why we don't have any other freedom? It's fundamentally because of that increment operation is the same and is used by every natural number, right? From 0 to 1, from 1 to 2, from 2 to 3, it's the same increment operation. And it's exactly because of that, now this unit length must be the distance or the length of the segment between any two adjacent consecutive natural numbers, say between 3 and 4, that must be the same unit length. That's what we studied last time. Today we will talk about something really exciting, and that is how we will actually, building from the very definition of natural numbers, goes to the very first arithmetic operation. So at the end of last lecture, we only defined natural numbers. We did not have anything else. But today we will add the first and perhaps the most important thing about numbers, and that is the addition. Okay? So you may wonder why we want to study number line and why it's so important, and perhaps more significantly, why it's so helpful. This is the number line we just drew. For now, we will only look at the positive numbers. So we will not even look into the left of the 0. That will come later. Okay? So we want to, and this cannot be emphasized enough about number line. First, I urge you to take this as a choose. We will be able to somehow prove this later, but for now, you do need to take a face value of the truth of this statement. So fundamentally, the number line is about all the so-called real numbers. So you still don't understand what real numbers are, but that's okay. You just need to first take a face value of this statement. The points on this number line and the real numbers, they have a one-to-one mapping relationship. Okay? For now, you just want to know this fact. You don't have to know what exactly this means. That will come later. Now, this is the important thing that we'll discuss today, right? Just look at those unit lengths between two consecutive natural numbers. The length of a line segment on the number line also represent a number, and that's a positive number. So we have not even talked about negative number, but we want to emphasize, to be accurate, it's not a negative number. So what is exactly the length of a line segment? Well, for now, because we have only defined natural numbers, so you can see that on this number line, we only have those natural numbers marked. Anything in between, they are numbers. We just have not defined them what they are or studied them yet. But it's not that difficult. You can imagine that on this number line with 0, 1, 2, 3, if they say there's a line segment, the line segment doesn't have to start and end at an integer number, right? You can pick any point, say this is a line segment. Okay? We still don't know what exactly this number is or this number is. All I can tell you for now, both are some numbers, and they're both real numbers. If you are lucky, they could be some rational numbers, like say for this one, could be hmm, could be 7 over 5. That means 1 plus 2 over 5. If you know fraction, that sounds about right at this point, right? But it could be this point is actually square root of 2, which will be irrational number. Anyway, you must jump a little bit ahead of yourself to think when we say there's a line segment here, does this line segment, the length of the line segment also represent a number? Yes, it does. Okay, that's something we will try to understand today. So the length of a line segment also represent a number, and actually a positive number. So that's why we can use the number line to study numbers and explain a lot of things about numbers. So the number line is an extremely important concept and also extremely useful tool for us. Okay, so the next thing we want to talk about is algebraic notation. If you did the first and the second homework, which you should always do, there's no way to study math without doing problems. Unfortunately, in this country, all the public schools give you very little amount of homework. And I believe for the first 3 years, from kindergarten to the second grade, probably 95% of students never get any homework. And that's just ridiculous. All right? You have no way to be a good, strong math student without doing a lot of homework problems. Let's just say problems. So first important thing you want to memorize for this class, do the homeworks. So in the first homework, I give you some really just kind of fun filling in numbers, right? And I gave you a lot of asterisk questions like, can you use a explain this or just explain this pattern in the mathematical language, something like that. What we really want you to do at that time is to think about a way to describe a particular pattern that you observe in a sequence of numbers in an algebraic way. And we will quickly learn this, why we want to do that. And in grade 5, it's usually considered too early for you to study algebra, but we are not actually studying algebra yet. We are just studying or getting familiar with algebraic notation. And that should be okay. So algebraic notation, why we are doing that, just consider a simple example here. We just say, go to our line segment case, right? So let's just say we pick an arbitrary endpoint, but only with natural numbers. Okay, so if we start with 0 and pick point 3, what is the length of this line segment from 0 to 3? We generally will use this notation, 0, 3. This is a square bracket. Now we use a bar over it. This is our notation that will be used in this book and in this class. We generally say this is the line segment. The starting point is 0, and the ending point is 3. How long is this line segment? Well, clearly it's just 3, right? Why? We start from 0, we just count. We just do counting. Actually, this is how natural numbers was defined in the first place. Remember how we mark rows 1, 2, 3? It's based on natural numbers. But how were natural numbers defined? We just define them in a continuously counting forward way. So we can see that from 0 to 1, 1, 2, and 3. We add this point. So now we know the length of this line segment is 3. But how can we describe this phenomenon? Say you have a line segment, the beginning point is 0, the end point is 3, so it's length 3. This sounds very trivial, right? It is, perhaps, it's trivial. But how about 4? Well, you can do the same thing. Say if you have a line segment from 0 to 4, the length of this would be 4. Okay, perhaps we should add a length operation here, but to make it simple, we just write it this way. But you should understand what we mean is the length of this line segment 4. It's not this is the actual number. The length of this segment is a number. But 4 is just another one, right? How can you represent all the natural numbers? Do you really need to enumerate everything here? There's no way you can finish that job. You can spend your rest of your life doing this and still cannot finish the job. So the dilemma here is that there are infinitely many natural numbers. How can we describe this property in a very easy way and without having to enumerate all of them? And that's exactly why we want to use symbolic notation or called algebraic notation to do the job. Okay? So if this is a problem, then the solution is to use the algebraic notation or symbolic notation. They're kind of synonyms. Sometimes we use one or the other. So we cannot enumerate all cases about the property, but we can use the algebraic notations to represent them all at once. Okay? So that's where this property is stated. We call it a theorem. A theorem is different from axiom because, like we said, for axiom, we just take it as true without actually proving it. Usually those things are so just kind of making sense, so obvious, and there's no way you can say this is actually not the case. Everybody should have zero amount of doubt about those statements. On the other hand, the theorems, they can be proven, meaning that they usually, we start with some definitions or axioms, then through a very rigorous process, logical reasoning, and to show the statement is actually true. Okay, so this is our first theorem. And it's about what we just discussed, right? If you have a line segment starting at 0, the endpoint, whatever that number is, it's always exactly the length of this line segment if you write in a way like this. This is true for 3, this is true for 4, and this is true for any number. Maybe 1 billion, maybe 1 billion plus 10. It doesn't matter what that number is. But how do we represent this idea in a mathematical way? This is the algebraic notation or symbolic notation. We just write this length in a general way from 0 to m, and with understanding that m, where m is any natural number except 0. So if m is 0, it's a special degenerate case. But at this point, we don't want to confuse you too much. So let's just agree m is always greater than 0. It can be 1, can be 2, can be anything. But we want to use a symbol here. It's a letter in the alphabet, m, to represent this number. So we essentially agree m can be any number, any natural number other than 0. So in one shot, we covered every possible natural number. And this is exactly called symbolic notation. We use a symbol, which is m here, to represent a general number. Can be anything. So it looks very simple and very trivial, but congratulations, this is the first step of learning using um, symbolic notation or algebraic notation. So what this theorem says that is a very trivial one, right? We just saw that. The length of the line segment from 0 to a natural number m is m. Okay? So the length of this line segment is exactly the value of the point at the end. That is m. And you may think about why this is true. Why is it's a coincidence? It's just m. It's not a coincidence. It's actually because the starting point of this line segment is actually 0. Okay, this is sounds trivial, but the mathematical ideas embodied in this theorem is not trivial at all. So we will lay down another important property, and this is based on some motivation or some questions you may have about theorem 1.4.2. Yes, I understand why this line segment, the length is exactly the last number or the second number in this line segment. That's exactly because the first one is 0, right? So now you may want to think, well, what if I have a line segment that begins at another natural number, but it's not 0? And of course, because now we only have natural numbers, nothing else. The ending point, the second one, must be also a natural number. So let's consider this. That's actually very legit, actually very excellent question. So we consider from 0, say, if we can make this a little bit longer, we can mark so that we can mark more point, 4, 5, and I guess 5 is enough for this purpose. So if we start at 1 and mark the second point as 4, so the notation will become 1 and 4, right? So first of all, we agree this is a line segment. And what is the length of this? Well, you may say, that's trivial. 4 minus 1 equal to 3. Everybody should know that. If you're a second grader, you should know this. Just by looking at starting at 1 and at 4. But there's a big problem in your argument. And what is that? What is exactly is this animal 4 minus 1? Come on, guys. We have not even defined what is addition. So we certainly do not know what is 4 minus 1. What is that? We don't know. We have not defined any arithmetic operations. And as you will learn later, subtraction is generally just another way of saying addition. They are not two independent, unrelated operations. Subtraction is just the inverse of addition. So that's why if you learn advanced algebra in college, you can see that we do not define 4 addition, subtraction, multiplication, or division. We only define addition and multiplication. Subtraction is actually the inverse of addition, and division is just the inverse of multiplication. But that's for another day, maybe a long road down there. So you won't encounter that until even in this lecture will be quite a few weeks later. But so now we actually do not have subtraction available. So what is the length of 1 4? Well, there's only one way to know the length, and that is perform a counting process. So that is how we start at this point 1. This is the beginning point of the line segment. We do a counting 1, 2, 3. We get the ending point 4. Therefore, we know the length of this line segment 1 and 4 is exactly 3. In fact, fundamentally, that's the only way we can know for now. Okay? So, from 1 to 4, the length is 3. But you may want to make this argument. Can we say this red line segment is from 1 to 4? It's just another version of the one we first look at, which is from 0 to 3. Can we say this red line segment is just the blue one, which slided to the right by 1? This actually is not a trivial question. Yes, in generally, we should agree this is just a slided version of 0, 3, which is right here. We initially start with. If we move it or slide it to the right, so that if 0 move or slide into 1, wouldn't 3, that point, slide into 4? Obviously, you would say this is so obvious, right? You're right. It is obvious. But because it's so obvious, we cannot actually prove it. How do you prove it? This is true. Why this is true? Actually, you cannot prove it without making additional assumption, and that is this one. This one, we actually take it as an axiom, and this is the proposition 1.4.3. We say that when you slide a line segment on the number line, so sliding a line segment on the number line does not change the length of the line segment. Pause for a second to think about this statement. Isn't that obvious? When you say slide this line segment, it's not made by something that is kind of bendable. When we move this line segment 0, 3 to another location, if the beginning point goes from 0 to 1, why would this change? Well, we have to agree it doesn't change. It can change in theory. Why not? Why not it cannot change? That's something we don't know, and we can never say it will not change. The only thing we can say is let's agree this will not change. Okay? Actually, if you think about very advanced physics, we have not studied, this is not necessarily true in the real world. When you measure something at a location, say at the equator somewhere, when you measure that something, the same thing, you transport it to the say North Pole, you actually may find that measurement does change due to the physical world limitation. So although math is an abstract, just imagined, idealized world, it does not have to be really correlated to a real physical world. But in theory, there's nothing prevent this say 0, 3 when you slide it on the number line, it actually changed. We just cannot know. So we have to agree this will not change. Okay? And this is very trivial but very important to understand that in math, we have to discuss about things in a very rigorous way. Otherwise, the whole building will collapse. So let's agree that when we slide the line segment on the number line, the length will not change. Now we are ready to define what is addition. Okay, everybody learned addition 3 or 4 years ago, right? But I know some of you, your parents push you so hard, you learn addition even before preschool, meaning that maybe you learn it at the age of 3. I personally don't think that's a good idea, but maybe your parents thought that was a good idea. Anyway, what is addition? What is exactly addition? Well, you may say, yeah, I know addition. Addition means that 3 plus 5 equal to 8, 8 plus 9 equal to 17, yada, yada, yada. Yes, I know addition. You're right. You did it correctly. But what is it? What does this mean, 3 plus 5 equal to 8? Did anybody actually tell you what it means? Well, that's just true. But why is it true? So, this is actually not trivial. I assure you, if you ask all the adults in America, out of 10,000, you'll be lucky you can find a couple that can really answer this question. Addition is actually something we created, we define it without agreeing on what addition is. We cannot actually just show a lot of things. So, based on the way we define the natural numbers, we are now able to define what addition is. But consider the simple problem, okay? Let's assume for now you forget about anything related to addition. You just don't have this concept of addition. Let's just wipe that out in your memory for now. Maybe for the next 20 minutes. Well, we have this problem. You have 5 apples, you have 3 bananas. You know it's exactly 5 and exactly 3 because you have already count both. You count 5 apples, 1, 2, 3, 4, 5. You count the bananas, 1, 2, 3. Now I want to ask you how many fruits you have in total. Well, what can we do? Remember, you do not have addition. You cannot say 5 plus 3 is 8, even it's correct. What can you do? We do have numbers. We know 1, 2, 3, 4, 5, 6, 7, 8. But even we know 5, in this case for the apple, and 3 for the banana, we don't know that the total. And we don't have something like addition. In that case, your only choice is to count again by putting them together, lining them up like this. But you don't have to start from the very beginning. The trick here is that you can be a little bit lazy. You can take a shortcut. That is, you don't have to count from the very first apple. You can count after the last apple. Why? Because you already know you have 5 apples, right? We already count that. We just don't know how many in total we have. And even we know there are 3 bananas, we still don't know what the total is, the aggregate total. Because of that, we have to count them together again. Well, again, we have never did that, so I take that back. Not again, just that we have to do some additional work. So we line them up like this. We start with the last apple. We know this is number 5 because we know there are 5 apples. Now, with the 3 bananas lined up, we know the next one, the very first banana, is number 6 for the fruit. Not for the banana, not for the apple, but for the fruit. This is number 6, this is number 7, and this is number 8. And we have counted everything. Now we know the total is 8. think about this again. Let's just say you go back 6 years ago. You learned nothing about addition, but you did learn how to count 1, 2, 3, 4. And I told you, and you tried, there are 5 apples. Yes, you count them 1, 2, 3, 4, 5. And you count 3 bananas 1, 2, 3. Just imagine you go back to that early day. Now, if I ask you, or your mom asks you, Ben or Lisa, how many fruits you have in total? What will you do? You will do exactly what I just did. You have no concept about doing addition. The only way you can find out that total is count all together again. But if you little bit just kind of curious, you don't have to start from 0 and 1. You can start from 5, but you still need to count the bananas one more time, essentially, because now it's an aggregate. It's about the total. So therefore, this is the only way to know the total at this point. We don't have any addition. And that's actually how addition is defined. Addition is nothing but counting. Okay? So, we actually define our operation, this weird operation addition, in this manner. If we have 5, and by the way, when we say add 3 to 5, we write it this way. 5 goes first, 3 goes second, meaning that the beginning one, the one you have is put first. 5 plus 3 is defined as we start at 5. That's what you already have. We increment 5 3 times. So we apply this increment operation upon 5. Then again, now it's on 6, the result of increment 5. Then again, that will be on 7. So 5 plus 3, it's actually defined this way. You just don't know it yet. Never told by anyone. So our addition is literally defined this way. We apply this increment operation on 5, starting at 5 3 times. Why we are doing this? Because this is the only thing we have. Remember how we define the natural numbers? We start with 0 and with the increment operation. That's about it. That's our starting point. That's why this 0 and 1 dudes both are super important. 0 gives us a starting point for the counting, and 1, the very concept of 1, signifies this increment operation. And with those two, a 0 and an increment operation, we can define all the natural numbers. And actually, addition comes from this definition. So from this point on, you should recognize that addition is nothing but just counting. Okay? So this is how we would explain this on the number line. We already did that, but let's go through one more time. We start with 5, right at this point 5. Now somebody told me, hey, perform this operation 5 plus 3, which means that you need to quote unquote add 3 to 5. But I don't know what the heck add 3 means. The only thing I know is to counting. So I will start from 5, count 3 times, meaning that counting forward 3 times, increment by 1. And from the definition of natural number, we know the next one is 6. Do it again, 7. Do it again, 8. That's about it. That's exactly what addition is all about. Okay, so let's just emphasize this one more time. Addition is nothing but repeated counting forward. Okay, but now we want to give it a more rigorous definition in terms of mathematical language, and we now know we want to use our friend symbolic notation, right? Because we cannot possibly enumerate all the cases of addition. like 512 plus 3031. There are just infinitely many such cases. So we want to use symbolic notation to capture the essence of all those additions. So let's say addition is an operation that requires two numbers, right? A first number, a second number. So let's say that m and m be any natural numbers. This is a big qualification, meaning that for now, our addition only works for natural numbers, not even including negative numbers. That will come later. So with rows, we define this operation using this plus sign because we just pretend that we forgot everything about addition. We do know everybody is using this symbol, so why don't we use it the same way? If you choose, you can choose another symbol, but you will make yourself look ridiculous, okay? So let's just say we define this plus operation over m and n. It's defined this way. So m plus 1, it's just the increment definition we have. Remember, we have a set of axioms, and that's the very first one we have, or second one, I'm sorry. 0 is the first one. We start from that point. There exists an increment operation on any natural number that generates a different natural number, which is next in counting to the given current number. The next one, for example, 4, 4's next is 5, 5's next is 6, and so on. And this is the increment operation we all agree we should have. So at this point, when we define addition, we will say m plus 1 is just applying this operation on m. And this will give you a result, right? This is an operation. So m plus 1 actually has two meanings. One is the operation itself, and one is the result of this operation. So the result is the natural number next to n. This is exactly what we said for increment, right? Now, what is m plus n? Well, once we have this first step, you can imagine after adding 1, you get a new number, which is m plus 1. But you can repeat this same process, right? M plus 1, oops. Once you have m plus 1, m plus 1, that's the first step. And I'm abusing your knowledge. I'm assuming that everybody knows a little bit about the parentheses. This is just m plus 1 we just did. But this new number will be able to do this again, plus 1 again. And this new number can do yet again. So this can continue. And that's exactly what we say here. When you have this thing m plus n is another natural number, we just repeat this process n times. And that is our definition of m plus 1. M plus n, I'm sorry. And this is the true meaning of addition. You can, without too much just hesitation, you agree this is nothing but counting, right? So m plus n is just counting. We start from m, counting forward n times, where both m and n are natural numbers. So if you may ask about some corner cases, what if n is 0? Remember, 0 is also a natural number. Where n is 0, it simply means that we don't do anything, right? We say that perform is plus 1 n times. If it performs 0 times, that simply means that we don't do anything. So by definition, this m plus 0 simply means m. You may think this is trivial. This is actually super significant in algebra. We add anything to 0, we get anything back. This is so important. This is explained in the context of natural numbers because you don't do any counting forward at all. You just stay right there. You remain stationary. Of course, you are still yourself. You have not changed a thing yet. Maybe you stand there for 5 years, you'll get a little bit older, but you are still yourself, right? So if you don't do any counting forward, nothing will change. So this is our definition of what addition really is. Okay? So that means that we have essentially, truly defined addition as a counting. But remember earlier, we had that apple banana scene. If you did nothing but a game of renaming, you essentially renamed counting as addition. You did not get anything new, right? Well, yes and no. Because now we characterize addition as an operation with two numbers. That's something different. Remember, in the counting process, we only have one increment operation. That's about it. And the increment operation can only apply to a single number. That's why you go from 5 to 6, from 6 to 7. But now, with this addition operation, we have two things to work with, right? We have a starting point, we have a number of steps that we have to move forward, and that is significant. So, as we'll learn in maybe 2 or 3 weeks, addition can really enable accelerated counting. Otherwise, our banana apple counting um, example will really piss us off. Think about this problem. Yes, we know from 5 and 3 we cannot do addition yet. We have to do counting. But even if we can't do addition, this addition is actually defined through counting. What else did we gain? We gain nothing but get a new name, right? Get a new name. Let's just say if we have 5,000 apples and 3,000 bananas, I have already counted the apples. There are 5,000 apples there, and the bananas, 3,000 bananas. What is the total? I don't have addition. Oh, okay, we just had addition, but addition is just counting. That means that we don't have to recount all the 5,000 apples, but from that point on, 5,001, 5,002. We still have to essentially recount all the 3,000 bananas to get that total 8,000. That would be ridiculous. Nobody wants you to do that, especially you have already counted 3,000. So, yeah, even as a third grader, you can safely tell the total is 8,000. But why is 8,000? Where did you get that 8,000 from if you don't do counting? Think about it. Yes, I do addition. So how do you do addition in this case? Let's get rid of all of them. Let's just with that example. If you have 5,000 apples and you have 3,000 bananas, and we know when we put them together, we have 5,000 plus 3,000, and we know this is 8,000. But how did we get actual 8,000? We certainly did not put them on the number line or really purchase that many apples and bananas, line them up, actually count them. But how did we get this? If you recall, essentially we did this, right? This is the vertical thing, vertical addition. Of course, those numbers are pretty silly in the sense that we got all the zeros. You can directly write that down. This is 8 because everything else is 0, so you can get 8 down 0. But imagine this number is a little bit more complicated. Instead of 5,000, we get something like this. And this could be, say, 6. And it's like this. How do you do that? You have to actually perform the vertical addition process. This is actually a brilliant algorithm. So 5 plus 9, 6 plus 9, that's 15. We put 1 there. And 2 plus 0 plus the carry 1, that's 3. 2 plus 7, that's 9. And 3 plus 5, that's 8. So we know the total now is 8,935. Cool. Very easy. Why this was even possible? Why can we do addition this way? That's a much, much deeper question than you actually imagined. Okay, that's what we will study in a couple of weeks. But remember, in the second homework, I did you actually do things like this and focus on one question is that during this process, what you actually need to remember. You do need to remember things like what is 6 plus 9? What is 6 plus 9? That's 15. I'm pretty sure you did not use your fingers, use whatever to actually count 9, 10, 11, 12, all the way to 15. I'm pretty sure you did not do that, right? Because you have been working on those addition problems, decimal systems for so long, you should, and probably you did, memorize 9 plus 6 is 15. It turns out when you do this vertical addition algorithm, all you need to remember is things like 1 plus 1, 1 plus 2, 1 plus, 1 plus 1, 1 plus 2, and all the way to 1 plus 9. And then 2 plus 2, 2 plus 3, 2 plus 9. And continue until you hit the last two, say a plus 8, a plus 9, and 9 plus 9. If you can see that, this is actually a triangle. It's a triangle. It's very similar to the multiplication table, but that's the thing that you actually need to memorize if you want to perform this general algorithm, vertical addition, without resorting to any type of counting on the fly. Because once you memorize this triangular table, which has exactly 45, if you count that, that's 9 plus 8 plus 7. By the way, we discussed this during our first enrichment class last Saturday, right? This is so important. Everybody should understand how to do something like this. 1 plus 2 plus 3 to any number. What's the formula for that? And we know 1 plus 2 plus 3, 1 plus 2 plus 3 plus all the way to 9, that's 45. There's a formula for that. So you only need to memorize those 45 entries in order to perform an arbitrarily large vertical addition without doing any actual counting. This is definitely brilliant. You think this is easy and simple only because you are asked to memorize this process without giving the deep thinking why this is true. So we won't be able to discuss this until we studied the place value system, which is essentially the same thing, say the decimal number system or Hindu-Arabic decimal number system, and together with some laws like a commutative, associative with those laws, which we'll study in the next couple of weeks. But for now, I want you to treat this very seriously. You don't think this vertical addition algorithm a very trivial one. Maybe you learned it in the second grade, but this is really a brilliant thing. Without it, guess what? We have to count everything. Without this thing, we will have to count large things like when we have this many apples with this many bananas. What is the total? You have to count all of them together. And why this actually works? A part of it is because of this place value system, the brilliant Hindu Arabic decimal system that make together with the addition operation we just defined, those two things, the decimal place value system and the addition operation we just defined as a counting, make things like this happen. Okay? I will see you next time. Friday. Bye. Oh, by the way, read the handout. You have to read this handout perhaps more than once. If you read 3 times to understand the materials, you are pretty smart. Okay? I will see you next time. Bye.